Thank you. Okay, I'm being recorded. Okay, continue. Yeah. Well, thank you for the invitation to give this talk. I was hoping I'd get to go to Toronto, but I guess that will have to wait for another day under the circumstances. The subject I'm going to talk about, topologically ordered matter and why you should care, is a subject that cuts across a number of different fields of physics and a number of different fields of science as well. In condensed matter physics, I'm a condensed matter physicist, topologically ordered matter is one of the modern themes that comes up very frequently, and it sort of pervades much of modern physics. But it also occurs in quantum information and quantum computation in the form of error-correcting codes. And in the field of high energy physics, many of the ideas of topologically ordered matter is where they originated in the language of topological quantum field theories and people studying quantum gravity. The field is also relevant in mathematics, people doing low-dimensional topology and knot theory, and also in computer science, particularly people thinking about quantum computation. So it's a field with a lot of different aspects and a lot of different people who are thinking about it. And the origins of the field go back quite a long way, a surprisingly long way. And I'm going to start at its roots, which are in the 1800s. So in 1867, there were two very well-known scientists in Scotland. One of them by the name of Lord Kelvin. I'm sure everyone knows, so I don't have to tell you all the great things he's done. And then he had a close friend who people probably don't know by the name of Peter Tait. Tait and Kelvin worked together on many things throughout their lives. And in 1867, they were interested in a phenomenon of fluid flow, actually. It was a phenomenon that people in the 1800s were very familiar with. It's the phenomenon of a smoke ring. So let me just draw a smoke ring, remind you what it is. So it's an invisible ring in the middle of the air, and the smoke or the air circulates around that invisible ring, sort of this way, and then the whole ring comes out of the plane of the board at you. Now, in the 1800s, people used to do this very strange thing that made them familiar with smoke rings, this thing called smoking tobacco. They don't do that anymore, so we're not familiar with it, but I'm told it's something like vaping. So the thing that's really hard about giving a Zoom seminar is you don't know if people are laughing at your jokes or not. But I think I can probably assume that no one's laughing because none of my jokes are funny. But anyway, no, but people were familiar with the idea of a smoke ring, but no one had really studied it in detail. And Peter Tait wanted to study in detail. So he built a machine that would produce smoke rings, and he showed it to his friend, Lord Kelvin. And Kelvin had a number of simultaneous epiphanies. Wow. And some of those epiphanies are things that we still teach to undergraduates. One of them is known as the circulation theorem. And the content of this theorem, well, okay, it can be phrased in several ways, but one way to phrase it is to say that if it were not for the fact that air is not a perfect fluid, then this fluid flow configuration always flowing around that white ring, the fluid keeps flowing around and around and around, that would go on forever. The only reason that fluid flow configuration ever stops flowing around and around is because air has friction and viscosity, and eventually the energy is lost, and eventually it stops flowing. So this was his first epiphany, and that got him thinking about a second epiphany, which is where can you find a fluid that has no dissipation, no friction? And such perfect frictionless fluids, they do exist. We call them superfluids. For example, helium at very low temperature. But Kelvin didn't know about temperatures that low, really, because they didn't have any sort of cryogenic apparatus. And he didn't know about helium either, it hadn't been discovered. So he certainly didn't know about superfluids. But there's a famous mistake in the literature, which was supposedly a fluid with supposedly no dissipation. And Kelvin believed in it. And let me remind you about this famous mistake. It's called ether. So ether was supposedly a perfect dissipationless, frictionless fluid, and its purpose was to carry electromagnetic waves through the environment. Now, why did they believe in this stuff? Well, they believed in this stuff actually for pretty good reason. They knew a lot about waves, and when they saw a wave in the water, they realized what they were seeing was actually water sloshing back and forth. And when they heard a wave of sound in the air, they realized that what they were hearing was air moving back and forth. Now they knew that light had wave-like properties, it was a wave, and they didn't see anything moving back and forth, but they hypothesized that such a material must exist, and they called it ether. Actually, the idea of ether goes back several hundred years before Kelvin and Tait to the philosopher René Descartes, who thought this stuff up. He said, I think, therefore it is, and he created ether. That was another joke in case you didn't get it. It actually is due to René Descartes. And it seemed very convincing to all the scientists of the 1800s, and everyone believed in this stuff called ether. And they knew that this ether stuff had to be extremely dissipationless because you can see light from stars very, very far away. And if there had been any dissipation or friction in the ether, the light wouldn't have gotten to you. So on the one hand, Kelvin believes in this ether stuff. On the other hand, he has this circulation theorem that tells him if you have a fluid flow configuration and perfect dissipationless fluid, like this fluid flow configuration, it should last forever. It should be completely stable. So that got him thinking, what then is the meaning of this fluid flow configuration in the ether? And he said, well, this fluid flow configuration is an atom, like a hydrogen atom. And then he could have something more complicated, like you could have two linked rings, like this, and the fluid would flow around this linked ring this way, and the fluid would flow around this linked ring this way. And by his circulation theorem, this would be completely stable for all time, and it would keep flowing and flowing and flowing. And maybe this is something like a hydrogen molecule. And you could have something even more complicated, maybe something like this. And let's see if I can draw this without making a mistake. Like that, knotted line like this, and the fluid would flow around it this way and around it like this way. And this would be, by a circulation theorem, this would be completely stable. It would last forever. And maybe this is a more complicated atom, like maybe lithium. So this theory of what makes atoms was known as Kelvin's vortex theory of the atom. It sounds completely bonkers to us right now because we know that, well, first of all, we know that ether doesn't exist. It was disproved by Einstein, of course. But we also know what makes up atoms, and it has nothing to do with any sort of fluid flow in the ether. They're made of, protons, electrons, and neutrons. But it actually sounded really good to people in the 1800s, and a lot of very serious scientists took this seriously, and they really thought that this might be what causes atoms. And one of the people who took it extremely seriously, although originally he criticized the theory, eventually he decided that he liked it, was Peter Tait. And Peter Tait felt that what he really needed to do in order to understand this vortex theory of the atom properly was to build a periodic table of all possible knots. This is the simplest knot. This is the next most simple knot. This is the next most simple knot. And so he devoted a large part of the remainder of his life to developing a periodic table of the knots, really trying to understand knots and make a table of all possible knots and which ones are different from each other and which ones are the same. And he thought if he could do this, he would understand something more about the periodic table of the elements. So Peter Tait is viewed as the father of the modern branch of mathematics of studying knots, known as knot theory, which is a very rich and beautiful branch of mathematics and topology, and a very important branch of mathematics and topology. Tait was way, way ahead of his time in many respects. Some of his conjectures on knot theory were not proven until after the year 2000. So anyway, I'll tell you a little bit about what it is that Peter Tait discovered that turns out to be important for physics. But before doing so, I should probably tell you the end of the Peter Tait story because it's a rather sad end. So Tait, around 1900, he's spent a great part of his career working on building this periodic table of the knots, what became known as the Tait table. And he realizes he's no closer to understanding the periodic table of the elements. So he writes some letters to his friend Lord Kelvin, and he's rather upset about the situation, feeling like he's devoted so much of his productive career to a theory that just isn't going anywhere. Then in later that year in 1900, he had a son, Freddie Tait, and if anyone's a a huge golf fanatic, they'll know the name Freddie Tait. He was a champion of the British Open. Peter Tait was also a wonderful golfer, actually, and he wrote some beautiful papers on the flight of golf balls. Freddie Tait was killed in the Boer Wars in South Africa. And that put Peter Tait into a deep depression, and he never recovered. He died just a few months later. So Peter Tait died very sad, and a really terrible ending for someone who is really a great scientist. So what is it that Peter Tait understood that turns out to be quite important for us later on? So Peter Tait put his finger on what is the fundamental question in the theory of knots, and it's a simple question to phrase. So let me give an example of it. The question is, suppose I have two pictures of knots, like this one and like this one. How do I know if these two pictures represent the same knot or if they're different knots? In other words, can this picture be deformed into this picture without cutting? You know, are they topologically equivalent or topologically inequivalent? Now, we're pretty smart, and we can sort of look at this, and maybe just in our heads, we can unfold this picture, unfolding this one this way and this one under this way, and we take this figure 8 looking thing, and it will turn into this simple open loop. So we say that these two pictures are really representing the same knot. They can be deformed into each other without cutting. So they're one entry on the periodic table of the knots, not two entries on the periodic table of knots. Now, this sounds like it's a really easy question, but it turns out when you have more complicated knots, it rapidly becomes extremely difficult to tell when two knots are the same and when they're different. For example, if you look at this knot here, the so-called trefoil, it was not until the 1920s that someone managed to show that the trefoil is actually topologically inequivalent to its mirror image. There are two trefoils, a right-handed trefoil and a left-handed trefoil, and they cannot be deformed into each other without scissors. So what Peter Tait realized is that you need some tool to help you distinguish knots from each other. And in modern language, what we call that tool is a knot invariant. Peter Tait never used this language, but it's clear that he understood it. So a knot invariant is a mapping from an input, which is a knot or a picture of a knot, to an output via a set of rules. And the output can be a number or some mathematical expression, a polynomial or something like that. That's not important what the output is. What's important is that the set of rules are cooked up in such a way that topologically equivalent knots have to give the same output. Okay, so if I have two really complicated knots, I put them into my set of rules. If I get two different outputs, I know immediately that these two knots are topologically inequivalent, that they can't be deformed into each other in any way without cutting. Now, to show you how this works, I'm going to give you an example of a particular knot invariant. The knot invariant often goes by the name of the Kaufman invariant, Kaufman bracket invariant, named after its inventor, von Jones. And that was a joke. It's not named after his inventor, it's named after Louis Kaufman. So von Jones he actually just passed away last week, and fairly young, rather suddenly, which is a terrible thing. But he's famous. He won his Fields Medal for his work in knot theory, and what he was doing, I mean, he did an awful lot of things in the field of knot theory, introduced a whole lot of new concepts. But what Kaufman did was at least as important, at least in my opinion, because he took the complicated mathematics that von Jones was doing, and he simplified it so much that I can explain it to you in about a minute, which is what I'm going to do. So to define the Kaufman bracket invariant of a knot, the first thing you need to do is you need to choose a number. A equals a number. I'm going to call it A. We'll leave it a variable for now, but we might give it an actual value later on. And then we just have two simple rules. The first rule is that a loop with nothing going through it, nothing going in the loop or across the loop or anything like that, just a simple loop sitting by itself, is given the value minus a squared minus a to the minus 2. So every time we have a loop, you can give it the value minus a squared minus a to the minus 2. And we can, that combination of variables comes up so often, we give it its own name, we call it D, okay? That's the easy rule. Here's the harder rule. If you have a picture of a knot with two strings crossing over each other, like this, you can replace that picture with two pictures. One picture where the two strings go vertically, and another picture where the two strings go horizontally. And then these pictures get prefactors. This picture getting a prefactor of A, and this other picture getting a prefactor of A inverse. Now, what am I doing here? I'm doing algebra with pictures. I'm taking a picture and replacing it with the sum of two pictures, and then the pictures get prefactors as well, algebraic prefactors. And if this doesn't make sense, I'll do an example to try to make it clearer. These are the only two rules we actually need, but I'm going to cheat a little bit and draw a third rule. And the third rule looks exactly like the second rule, except I'm going to rotate all of the pictures by 90 degrees. And the reason I'm doing that is because it's easier to draw the rule twice than it is to ask you to rotate your head at a later point. Okay, now to show you how this knot invariant works, how this Kaufman bracket invariant works, we're going to evaluate the Kaufman invariant of a very simple knot. Okay, so here's a very simple knot. Like this. Oops, try to draw it a little bit better. I want to draw it like this. It's this figure 8 looking thing. It's exactly the same thing I had up here. Drawn a little smaller. And I'm going to try to evaluate the Kaufman bracket invariant of this knot. How do I do it? Well, what you do is you focus in on this little region here in that red circle. And in that red circle, I have a crossing that looks exactly like this. So I can replace that area with A times vertical plus A inverse times horizontal. And then everything that was outside this little red circle just gets transferred over to the right-hand side, exactly unchanged as it is over on the left. Okay. Now here, I'm going to pause for a second and ask if there are any questions about that, because this is sort of the fundamental step. And if you understand this, you'll understand everything. This is the most important moment of the talk, most important moment of the day. Okay. Since question, you didn't give a rule for two disjoint knots. Yes, for two disjoint knots, you will just multiply together the result of the Kaufman bracket for each individual knot. Thank you. You're welcome. I like how this works. They just appear before me, these questions, they just pop up on their screen. Okay, anyway. What do I do with these pictures? With these pictures, I still have crossings, and I have to get rid of those crossings. So I'm going to use this lower rule, which looks like this crossing and this crossing. Okay, so let's do that. Try to do that quickly. Okay, so first of all, I'm going to take this A, move it down here. So A, I'm going to open up a bracket, and then I'm going to apply the rule. So the rule tells me I have A times horizontal plus A inverse times vertical, and then fill in the rest of the knot exactly as it is up here. So it looks like this, like that, and it looks like this, and like that. And then I'm going to move this A inverse down here. So I'm going to add A inverse and open up a bracket, and then do the same thing over here. So we have A times horizontal plus A inverse times vertical, and then fill in everything exactly as it is up here. So I have something like this, and 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 like this. Okay, so now what we have is we've gotten rid of all the crossings in our diagrams. And so now that I've let me try to just draw this one a little bit better. Oops, a little bit better, looks like that. Okay, so everything here has no crossings, and then I can apply the first rule up here, that the value of a loop is D. So we'll just reduce this now to algebra, replace every loop by a factor of D. So we get A squared times D squared, that's from two loops here, it gets D squared. Then A cancels A inverse. We have one loop, so that one loop gives you D. Then we have A canceling A inverse here, and 3 loops gives me D cubed. And then A inverse, and 2 loops gives me A to the minus 2 D squared. Okay, and then we need just one more thing, which is just a piece of algebra. Here it is, copy, paste, paste. If you recall, D is equal to minus A squared minus A to the minus 2. So I can put together this minus A squared and minus A, this A squared and A to the minus 2 to get a factor of minus D. So these two pieces put together here give me minus D cubed. The minus D cubed cancels. All I'm left with at the end of the day is D. That's the end of the calculation. Yay, everything is done. Okay, so why is this so exciting? Why does it get yay over here? The reason it gets yay is because I started with this kind of complicated knot and I got D. Now, why do I like that? Well, secretly, I know that this complicated knot was nothing more than a loop. And a loop is defined to have the value D. Now, I tried to make the loop look more complicated by folding it over, but still at the end of the calculation, I get D. And I could have taken this loop, and I could have folded it over 100 times, twisted it up and make it look really super complicated. And as long as I didn't use scissors, I didn't cut the knot, I would have still gotten D coming out at the end, okay? That's how knot invariants work. Doesn't matter how you present the knot, how tangled up it looks, if you can deform it back to your circle, it's going to give exactly the same output as a circle. So you can imagine how this tool, the knot invariant, is going to be very useful for Peter Tait or other people who are interested in trying to distinguish large complicated knots from each other. If you think about it a little bit harder, you'll realize that maybe it's not so useful. Why would it not be useful? Well, this picture here had 2 crossings and it ended up with 4 diagrams. If we had 3 crossings, we would have gotten 8 diagrams. 4 crossings would have given us 16 diagrams and so forth. So if we have n crossings, we would get 2 to the n diagrams, and total number of 2 to the number of crossings, crossings. Now, why is that a problem? The reason it's a problem is because it's really super easy to write a picture of a knot that has 100 crossings. And the number 2 to the 100th is so big that if you took the world's largest computer and you let it run for 1,000 years, it would never be able to enumerate all of these diagrams that come out. It would never spit out a result for this Kaufman bracket invariant. So for complicated knots, this is computationally difficult to come to an answer. And that is why it's maybe not so useful for complicated knots. And we'll come back to that in a moment. Okay. So after that large introduction to knot theory, let me switch topics completely and introduce something that sounds completely different, but is in fact exactly the same. It is the idea of a topological quantum field theory, or equivalent, almost equivalently, topologically ordered matter, These are almost precisely the same statement. A topological quantum field theory is a mathematical field theory that you write down on paper to describe a physical system. Topologically ordered matter is the physical system who is described at long wavelength and low energy by a topological quantum field theory. So basically talking about the same thing here. So what is the definition of topological quantum field theory? These are topologically ordered matter. This is a physical system where amplitudes, quantum mechanical amplitudes, are determined by topology only, not geometry. Now, let me try to put a little bit of flesh on that statement, that amplitudes should be determined by topology only. Okay, so let me draw some pictures here. Every physical system I'm going to talk about today is a 2-dimensional system. So here's a 2-dimensional disk. And we're going to have time running vertically. Time goes up because time is money. Money goes up. We'll imagine that our two-dimensional system, our two-dimensional disk, starts in its ground state, and then there's a gap to excitations. So basically, this is you can think of this system as just being an inert system with nothing interesting going on. It's just sitting in its ground state or vacuum state. Now, one thing you can do to your physical system to make it a little more interesting is you can add energy to it. And let's do that by sending in a photon. And that photon creates a particle-antiparticle pair, for example, like this. And maybe I'll send in another photon, create a particle. I guess in condensed matter, we call it a particle-hole pair, but you can also call it a particle-antiparticle pair. Create another particle-antiparticle pair. We'll drag one particle around another particle like this, and then we'll bring them back together at some later time and ask what happens when you bring them back together. Now, there's several things that can happen when you bring them back together. And one possibility is that they re-emit the photons that you put in here. Photon comes back out, and you get back to the exact same initial state that you started with, the featureless ground state here. But another possibility is that they form bound states, and the bound states refuse to annihilate back to the same ground state. Now, it shouldn't bother us too much that there's more than one thing that can happen and that the result is probabilistic, because we know in quantum mechanics that actually happens quite frequently, that, that you have probabilistic outcomes of various experiments. There's some probability amplitude of one thing happening, some probability amplitude of another thing happening. What's interesting about the topologically ordered matter is that those probabilities depend only on the topology of the knot that you formed, what knot you formed. So for example, I could take this experiment and I could change it a little bit by instead doing this. Oops, trying to make that connect up a little bit better, like that. And then maybe change it over here by doing this. And then maybe make this guy live a little bit longer by doing putting in the energy a little bit earlier, maybe down here, like that. And the probability amplitudes that you have at the end of the day when you do these experiments remain exactly the same. The probabilities amplitudes are in fact themselves, the probabilities are not invariants, Why? Well, the outcome of this experiment depends only on the topology of what you put in, and therefore it's a mapping from a knot as an input to an output via some set of rules in such a way that topologically equivalent knots have to give the same output. Therefore, this thing is a knot invariant. So this should actually surprise us a little bit that you have such physical systems that actually exist, because we're used to the idea in quantum mechanics that details matter. So things that matter is like how fast a particle moves matters, how close together the particles come to each other, how long a particle lives before you re-annihilate it. All these kind of distances matter. And here I'm telling you none of those things matter. The only thing that matters is the topology of, can you please clarify what the lines represent? So the lines, these are the world lines of the particles. So I'm drawing is a two-dimensional system, time running vertically. So I'm plotting the trajectories of the particle in 2+1 dimensional space-time. That's what thank you for the question. So the outcome of the fact that we have probability amplitudes that depend only on topology should strike us as being somewhat surprising. So this connection between topological quantum field theories, TQFTs, and knot theory was made very famously by Ed Witten in a very groundbreaking paper in 1989, for which he won the Fields Medal along with Vaughan Jones. Now, this paper has a lot of very brilliant things in it, But one thing that is in this paper is the following explicit statement. So the statement is that if you take a particular TQFT, or topological quantum field theory, known as Chern-Simons theory, I won't define exactly what that is. It's just a known type of topological quantum field theory. Simons is no relation to me. This actually is related. It is the Simons who is the billionaire financier, for whatever that's worth. Once was a mathematician, now a billionaire funder of science. Chern-Simons theory. So this Chern-Simons theory is a gauge theory. So we need a gauge group. So let's take the gauge group to be a simple group, SU2. We know SU2, you know, the rotations of a spinner. And then we need a coupling constant. We'll take the coupling constant, we'll call it K. We write it down here, sometimes called the level, the strength of the coupling. And K has to be an integer. So these were just known types of topological quantum field theories. And one of the things that came out of Witten's work was that if you want to get the probability amplitudes of all these particles reannihilating, all you have to do is you evaluate the Kaufman invariant, so probability of reannihilate. All you have to do is evaluate the Kaufman invariant squared for a value of A, which is given by, I guess, I e to the I pi over 2k plus 2, something like this. So you put in the right value of A into your Kaufman invariant and you square it and you get the probability that all the particles reannihilate. Now, perhaps more surprising still than this connection between topological quantum field theories and not invariants is the fact that these things are not just a figment of Ed Witten's overactive mathematical imagination. In fact, we can make sort of a table of different types of topological quantum field theories and the physical systems that we believe actually behave this way. So we'll take SU2 level 1, that's the simplest one. This is essentially equivalent, morally equivalent to U1 gauge theory with some radius. If you don't know what that is, don't worry. And the most fractional quantum Hall states fit into this category. So what I mean by this is that fractional quantum Hall states have interesting braiding properties when you braid their particles around each other. And even though people have believed this for 40 years, it's only been this year, very recently, that this has been shown experimentally, that you can actually take these particles, braid them around them, and see what happens. SU2 level 2 is slightly more interesting, slightly more complicated. There is one particular fractional quantum Hall state called nu equals 5/2. So just a label on a particular state of matter. Then there's, which is believed to be described by SU2 level 2. Then anytime you hear the word Majorana, it's basically equivalent to SU2 level 2. So there's lots of times you hear the word Majorana these days. Helium 3A film, superfluid film is one such case. We used to say that strontium ruthenate was one such case, but now it's starting to look like maybe it's not. But now there's some other materials that have emerged. Iron, tellurium, 0.55, selenium, 0.45, seems to be a Majorana material. Uranium, tellurium 2 seems to be a Majorana material. Then there's a whole host of engineered materials, materials where people try to put together materials with strong spin orbit coupling and superconductivity, and you sort of trying to design something that will behave as an SU2 level 2 topological quantum field theory. So there's been a lot of excitement about this recently as well. Then we can go up one level more to SU2 level 3, which is more sophisticated still. And there's only one state of matter that's ever been observed that's believed to be of this type. It's a fractional quantum Hall state labeled by 12/5 is its particular label. Okay, so these physical systems, we believe they actually exist. And let me, since I've used up a lot of time, and am I supposed to end on the hour? Is that, am I supposed to end more or less on the hour?
More or less, it could be a few minutes after.
Can be a few minutes after. Okay, let me try to give a description of some of the most interesting and most important properties of topological quantum field theories that make them particularly interesting. So let me draw a disk, a physical system here. Okay, maybe before doing that, I'll put, start the system in its ground state. Then I'm going to put some particles and antiparticles in the system. And so if I take most gapped systems from the ground state, and I say, okay, I'm going to start in the ground state. I'm going to put particles and antiparticles at some particular positions. You know, put creation operators, annihilation operators, creation operators, annihilation operators. I've told you what the wave function is by doing that. But this is not true for topological quantum field theories. For topological systems, or topologically ordered matter, you can have more than one linearly independent state, which I'll call 1 and 2, which have the same local descriptions. In other words, the local description of this is that you start in the ground state, and I add a quasi-particle here, quasi-hole, quasi-particle, quasi-hole. And yet I have two different wave functions that describe that. And how is that possible? Well, because you have to think about the space-time history of these things. And again, having time going upwards, I could have pulled these two particles apart from each other and these, or I could have pulled these two particles and these apart from each other. And these are topologically distinct. And so these two states, these two wave functions can be different from each other. So to prove to you that these are different, I have to take inner products. So to do that, let me show you how you take an inner product. Well, let me just draw up here the appropriate, so this is supposed to be the same picture again. Just not very good at drawing it. So here is now the bra associated with state 1. Just time reverse everything. And the bra associated with 2. Again, it's supposed to be the same picture, just my drawing's not very good. Okay, and if I want to take the inner product of one, some of these wave functions, these bras with the kets, I just squeeze them together to make a sandwich. So let me do that, make it a little smaller so you can see the whole thing at the same time. So let's take, for example, 1, 1. So I have the disk in the middle, 4 particles. I have 1 in the bra, in the ket, 1 in the bra. This makes 2 circles, and that's d squared. 2 circles gives you d squared. I can do the same thing for 2, 2. And that would give me, just really quickly, that would look like this. 2 circles is d squared. But if I take 1, 2, 1, 2, I would have, smaller still, I would have, well, 1 going down. So it looks like this going down, but it looks like this going up. Sorry, I did that backwards. This is 2, 1. 2 on the top, 2 up here, 1 here. Take the inner product of those, that looks like this. That's 1 loop, and that's D. So the fact that I have 2 wave functions whose inner products both with themselves is d squared, but inner products with each other is d, tells me I have 2 linearly independent states of the system, 2 linear independent wave functions, unless this d happens to be the number 1 or have unit magnitude, which is exactly what happens for SU2 level 1, but not for SU2 level 2 or SU2 level 3. But other than that, with that exception, you have 2 linearly independent wave functions, not just a single wave function. So why is this interesting? That was part of my title, and I promised I would tell you why it's interesting. Well, if I had called these 0 and 1 instead of 1 and 2, you would have immediately thought of a qubit, or a bit at least. And that is indeed why it is that people are interested in this. They want to use this kind of physics for a quantum computation. And the scheme of doing computation with this sort of topologically ordered matter is known as topological quantum computation. And it's also credited to 2 very smart people, Alexei Kitaev, who is one of the great geniuses of our age, I think, and Mike Friedman, who is a Fields medalist for his work on the Poincare conjecture. And the way they envisage doing computation with these particles is as follows. So you notice here, up here, I had a total of 4 particles, 2 pairs, and I had one 2-state system, 1 and 2 possible states. So it's 1 qubit. So if I want more qubits, I can make them. So here's my two-dimensional system, like this. If I want more qubits, so there's 1 qubit, here's another qubit. I'm always drawing time going vertically, like this. So there's a picture with 3 qubits, and I can make as many qubits as I want by pulling pairs of these particles out of the vacuum, pair creating. Now, if I want to do a computation of some sort, the way I do it is just by braiding the particles around each other in some well-designed braid, and we put a lot of work into designing braids that will do certain calculations. And then at the end of the day, you bring the particles back together and make some measurement of what comes out of these particles. Either they re-annihilate back to the vacuum or they do not re-annihilate back to the vacuum, and that's your measurement at the end of the day. So sorry for the messy looking picture. So there's 2 things I have to prove to you. First, that you can do quantum computation this way, and second, that you would want to do quantum computation this way. So first, that you can. You recall from the beginning of the talk that calculating the Kaufman invariant for a complicated knot is exponentially hard. If I have 100 crossings, it would take a computer 1,000 years to evaluate the Kaufman invariant. But if I had these particles in my laboratory, these Kaufman particles in my laboratory, I could make a measurement that would tell me what the Kaufman invariant is. All I have to do is form the knot in space-time, drag the particles around each other so that their space-time world lines form this knot and make the measurement. And you recall that the probability of re-annihilating is just the Kaufman invariant squared. Now, that means I just have to do the experiment many times and count how many times out of 1,000 the particles all re-annihilate back to the vacuum. And that gives me an estimate of the Kaufman invariant squared. Now, if you want it more accurate, you just do the experiment more times. So it's not actually calculating the Kaufman invariant, you're just estimating it, and you can estimate it as well as you like. Now you might say, well, that's still not calculating, you're just estimating it. But in fact, a classical computer couldn't even estimate the Kaufman invariant of a complicated knot in 1,000 years, whereas this computer can. So we have a very, very simple algorithm to make an estimate of the Kaufman invariant just by forming the knot in the space-time world lines and then seeing if all the particles re-annihilate, and that you cannot do with a conventional computer even in 1,000 years. So that convinces you that this computer can do some calculations that that classical computers cannot do. Now, you might say, well, I'm not interested in calculating knot invariants, but it turns out that it's not too much harder to show that the ability to calculate these Kaufman invariants is equivalent to the ability to do other so-called quantum computations, which enable you to do things like factor very large numbers or other things that people want to build quantum computers for. So that convinces you, hopefully, that you can do quantum computation this way. And then the other thing I should convince you is that you would want to do quantum computation this way. So to understand why it is that people are interested in doing quantum computation this way, you have to understand what's hard about quantum computation in the first place. What's hard about quantum computation is that quantum computers are exquisitely sensitive to any sort of noise that comes into your system, extra photons or phonons or something like that, that disturbs your computation. Now, what happens in this computation when noise comes in? Well, if noise comes in, what's going to happen is you're going to shake around the path of your particle from a nice smooth path to a kind of wiggly path. But as long as you don't change the topology of the path, you haven't done anything. You made any mistakes whatsoever as long as you don't change the topology of the path at all. So these topological computers are inherently robust against small amounts of noise. Now, So that explains why it is that people are interested in using topologically ordered matter for quantum computation. Now, the skeptic, and I will ask the skeptical question, so no one else has to. Will say, well, look, Google is already out there, and IBM are already out there. They're building quantum computers even right now, and they're not using this topologically ordered matter. So why is it that this is a better way? Well, Google may be doing the right thing and building their quantum computers, but they're going to need error correction. And it turns out that the best error correction known by a lot of measures is the so-called surface code, which to many of us is known as the toric code, which is basically a topologically ordered matter. It's a TQFT. So once you have your qubits, however you build them, the first thing you're going to want to do with them is build a TQFT to give it this topological robustness against noise. In the last, if I have 5 seconds more, I do want to say just a couple of things about the one case that we know extremely well that we've observed real topologically ordered matter, and that's fractional quantum Hall effect. Fractional quantum Hall. And here's a theorist picture of fractional quantum Hall effect. The theorist picture is you take electrons in 2 dimensions, 2-dimensional electrons, you add a magnetic field, and you cool it down to low temperature, and out comes, so cool, and out comes fractional quantum Hall effect. I hope there are no experimentalists watching me doing this, because they would really scream at me if they said that's all there is to it. But that's more or less how a theorist views it. And there are many different fractional quantum Hall effects depending on the ratio of the density to the magnetic field, made dimensionless by the flux quantum. So this can be numbers like 1/3, 5/2, 12/5, all these numbers that I was listing out. And these are all different phases of matter. Now, the claim is that this fractional quantum Hall effect is a topological quantum field theory. Now, for people who come from a high energy background, there's this paradigm in high energy physics that the high energy theory, some grand unified theory, is extremely symmetric. And when you cool down, you break symmetry and you get some less symmetric theory at low energy. And this is actually entirely the opposite. The high energy theory doesn't have any particular symmetry at all, but the low energy theory has a huge symmetry that has invariance under all sorts of deformations of space and time. So it's actually symmetry emergence rather than symmetry breaking. Now, the question we should be asking is, how do we know the fractional quantum Hall effect really is a topological? How do we know it's a topological quantum field theory? It's very hard to do any experiments on fractional quantum Hall effect. And really, most of the experiments that are done are just one experiment. And so I'll explain that one experiment. Here's your 2-dimensional system. It has some arbitrary shape. And the one experiment that's easy to do is you attach electrical leads to it, and you run a current between 2 of them, and you measure a voltage between the other 2. If you do the experiment this way, you measure the so-called longitudinal voltage, and the answer you get is 0. That tells you that what you have is dissipationless. You have a frictionless fluid flow. The one other experiment you can do is more or less the same, except you can cross the current and voltage leads to measure the so-called Hall voltage. Oops. Like this, and then jump over this guy and measure there. And then what you get is different. You get the Hall voltage, h Planck's constant divided by the charge of the electron squared, then 1 over nu, this is a ratio of small integers, p and q, like these integers here, times the current. And this coefficient is what you measure, is quantized to 1 part in 10 to the 10. I think that's better than measuring the distance from Oxford to Toronto within a centimeter. It's extraordinarily well quantized, telling you that something is protecting that experiment. And the thing that's protecting that experiment is topology. It doesn't matter what the shape of the sample is. It doesn't matter how far apart you put the leads from each other, where you put them on the edges, how you put them on the edges, what the leads are made of. You always get the same answer quantized to 1 part in 10 to the 10, which tells you something topological is going on. Now, the very last statement I'm going to make before I end is, what are these particles that we want to drag around each other? Well, the fluid is dissipationless. That means that we can have vortices in the fluid, and the vortices will be persistent. They should last forever, basically by Kelvin's circulation theorem. And it's these vortices that we want to drag around each other, these quasi-particles or vortices that we drag around each other. Now, if you think back to what Kelvin was thinking about vortices in a different dissipationless fluid in 3 dimensions. Whereas what we have here is the same dissipationless 2-dimensional fluid, and vortices in that dissipationless 2-dimensional fluid plus time. So we're still thinking about knots in 3 total dimensions. It's just one of our dimensions is time, whereas Kelvin, all of his dimensions were spatial. But at least morally, we still have the same picture that Kelvin had 150 years ago. So I'll stop there and I'll take questions. So there's questions come up here. If being topological makes things robust, then why are fractional quantum Hall experiments not easier to do? That's a very good question. So measuring the resistance is very easy to do. It's the thing that is hard to do is to pick up the particles and drag them around each other, because the particles have a fraction of the charge of a single electron, and the entire sample is buried deep inside a semiconductor heterostructure. So grabbing onto one and moving it and knowing that you've moved it has turned out to be much, much harder than we ever expected. Another question